Okay, good. You can. Okay. All right. Let's continue where we left off. Okay. We started talking about semiconductors, which is chapter 3. Okay. We're making good progress. We started looking at signals and amplifiers, chapter 1. Then we went on to operational amplifiers, chapter 2. Then we almost finished chapter 3, semiconductors, in the last class. In today's class, we're going to discuss diodes as well, chapter number 4. Okay. This is quickly what we reviewed in the last class. This is a review of what we did in the last class. Okay. There is intrinsic semiconductors, which are pure semiconductors and that do not have any impurities. In their most pure form, there is a crystal lattice structure of silicons sharing silicon atoms sharing their 4 valence electrons with their neighbors. Okay, so each silicon atoms um, at some time has 8 its valence shell fully occupied with 8 electrons. Okay, so this kind of sharing mechanism works out in the favor of silicon atoms that are trying to attain a low energy, highly stable state. Okay, this is attained by sharing or covalent bonds. And, um, there is no doping, there is no impurities here. Now, as discussed earlier, at the room temperature, when there is some kind of thermal energy, even in the absence of any doping, okay, some of the electrons are released from the valence shells, from the outermost shell, and they form free electrons. Their conduction band, they join the conduction band. They have enough energy to uh, transition into the conduction band. Okay, then so intrinsic semiconductors have just a few electrons at room temperature that are in the conduction band. As we saw earlier, this number in the order of 10 to the 10, 1.5 into 10 to the 10, even though it appears a large number, it really is a small number in comparison to the total number of atoms. So the total number of atoms, silicon atoms, is in the order of 10 to the 22nd, while the number of electrons or free charge carriers is only in the order of 10 to the 10. Okay, so that is Ni, intrinsic intrinsic um, charge carrier concentration. And then the number of electrons is equals to the number of holes. So we can calculate Ni squared. Okay, then we went on to how we can manipulate the resistivity or the resistance, how we can increase the conductance of the semiconductor by using an impurity, a dopant. Okay, if if I replace the silicon atom there with a group 5 element, the group 5 element, owing to its excess electron, 5 electrons in its valence shell, has a tendency to release that extra electron. It's rather easy to release that electron that is not in any covalent bond. Okay, so this significantly increases these extra electrons that are being donated by the um, donor impurities, by the impurities. They tend to contribute significantly, they tend to contribute to significantly increase the conductance. Okay, so typically phosphorus and arsenic are used as group 5 donor atoms. Okay, so there's an excess number of electrons in group 5 impurities. Group 5 impurities contribute to an excess number of electrons. Okay, then we looked at a an acceptor atoms that have only 3 electrons in their outermost shell, and they tend to take electrons from neighboring silicon atoms, and in the process creating a hole. Okay, so this hole behaves pretty much like a mobile electron. This hole is mobile. It can move around, jump around from bond to bond to bond. So acceptor atoms have 3 electrons in their outermost shell. They can accept electrons from other covalent bonds. Okay, very little energy is needed to free the extra hole, so it can conduct current. So these free charge carriers, which are holes, can conduct. So to summarize, the free charge carriers are holes in the p-type material, and the immobile, the extra electron, is the immobile charge carrier. That is immobile charge, not carrier, but immobile charge. The net charge is 0. Okay, then we went on to do a problem in order to look at the dopant concentration. Okay, let's see, in a pure semiconductor is doped to become an n-type silicon. Okay, n-type silicon, and then the dopant concentration, the amount of the impurity added, is given to be certain number, and then we were asked to find out the electron and hole concentration. Okay, this is n-type material, so the resultant number of electrons, okay, nn, okay, nn is much larger than the resultant. So this is the majority carrier. Number of electrons is much larger than the number of holes, okay, which is the minority charge carrier. Okay, so this is what we found in an n-type silicon. The number of electrons is in the order of 10 to the 17, which is the majority charge carriers, compared to the number of holes, which is Pn, given to be in the order of 10 cubed. Okay, then we went on to discuss about the p-n junction structure, simplified structure. And um, like I mentioned, if I bring together the p-type and n-type material, I get what is known as a p-n junction. And the electrons from one side diffuse into a low density area. Similarly, the holes from here diffuse towards the right because there is a lower density of holes on that side. So a natural diffusion phenomenon happens. Okay, and as a result, what happens is there is an excess of holes on the right hand side. While it is supposed to be n type, there is a migration of holes that creates a net positive charge on this side, and there is a migration of electrons from the right to left, which creates a net negative charge over here, creating what is known as a potential barrier. Okay, potential barrier. This potential barrier limits the further diffusion of holes and electrons. Okay, so that is the fundamental phenomenon that is happening as electrons and holes migrate from across the boundary here. When electrons migrate to the left and holes migrate to the right, they create a barrier to future migration, to further migration. Okay, so that's the idea of depletion region and a built-in voltage. Okay, we discussed the idea of a built-in voltage, which is about 26 to 25 millivolts VT. The thermal voltage defined as KT over Q. Let's remember this. This is our friend. We are going to see this 25 millivolts, 26 millivolts um, over and over again in the problems in diodes. Okay, so this thermal voltage VT is the built-in potential at equilibrium. Okay, so the built-in voltage calculated when no voltage is applied at equilibrium. Okay, shown on the leftmost figure is the built-in voltage. Okay, this is equilibrium, right? When there is no voltage, 0 volts applied between the terminals. Okay, if we do choose to apply some external voltage, that can be in this fashion where the negative polarity is connected to p-type, or it can be in this fashion where the positive polarity is connected to the p-type. Okay, this guy is called reverse bias, and this guy is called um, forward bias. This is what we discussed in the last class. Okay, in the reverse bias, the width of the depletion region increases and the diode acts as an off switch. It acts as an open circuit. Okay, in the forward bias, the width of the depletion region decreases and it acts as a on switch, a switch that is turned on. Okay, in the equilibrium. So in other words, this explains why when you had a triangular wave, okay, only some as the input. When you had a triangular wave in the input, the output was only um, the output was only active for certain duration. Okay, the rest of the wave just did not pass through. That's because during the positive half cycle, during this phase, okay, when the input was positive, during the upper half of the cycle, the diode was forward biased, okay, and then it let the input voltage pass through. On the other hand, down below, where the input polarity was negative, the diode was reverse biased and it did not let the current flow through. This is what you saw in the earlier labs. Okay, this is what we saw in the earlier labs. Okay, so that was the idea of forward bias and reverse biased diodes. Okay, so PN junction, that is reverse biased, um, and PN junction, that is forward biased. Okay, then we looked at the IV characteristics, current voltage characteristics of a diode. So there is a forward bias region. So this is the forward bias region, and as you will see, when the input voltage goes from um, the input voltage is shown on the x-axis and the current is shown on the y-axis. Okay, so we are interested in how the current changes as we increase or decrease the voltage. So that is all the idea of IV characteristics. Okay, and as you can see, in the forward bias case, okay, shown in the right hand side, in the forward bias case, what happens is the voltage increases exponentially. So this is an exponential curve. Okay, so the voltage increases exponentially, or the current, I'm sorry, increases exponentially with voltage. So the current has an exponential dependence on voltage. Okay, so as voltage increases, the current increases, and it does so in an exponential fashion. Okay, where Vt is the thermal voltage. Vt is given to be Kt over Q, where K is the Boltzmann constant, T is the temperature, Q is the charge of one electron. Okay, in the reverse bias case, the current is very small value. So in the reverse bias case, IS is the current, the reverse saturation current. As you can see, and I'm going to show the reverse bias current in purple. So this is reverse bias. Okay, this is the reverse bias where the current is really, really small. The IS is the reverse bias case, and this guy is the forward bias. Okay, in the reverse bias case, as you can see, this value is dependent on the area. Okay, the length and width of the diode times the intrinsic semiconductor. Okay, and there are of course the diffusion length LP and LN, the dopant concentration and the acceptor concentration. Okay, so there are different parameters that determine the IS, but the important thing that you want to remember is IS, which is this value. Okay, that guy is really small in comparison to um, the forward bias value. Okay, the reverse bias current is really small, typically in the range of nanoamperes. Okay, so in the reverse bias case, what happens is if you keep increasing the reverse bias potential, the reverse bias current only increases ever so slightly, but beyond a point, there is a drastic change. Beyond a point, there is a sudden and drastic change in the reverse bias current. Okay, this is breakdown region. So in other words, if you see the reverse bias current, which is shown in the lower um, quadrant here, this guy, lower quadrant here, okay, the reverse bias case, for a really um, large voltage, the current only changes slightly. So the current changes slightly, but suddenly the current begins to increase exponentially in the opposite direction. So if I were to take a diode, so let me reduce this. If I were to take a diode, okay, let me draw it a bit more carefully. If I were to take a diode, okay, and apply a negative bias, okay, a negative voltage to the P side and a positive voltage to the N side, okay, and I keep increasing the positive voltage and keep reducing the negative voltage. So I'm increasing the negative bias, okay. If I keep increasing this and keep reducing this, I'm moving towards the left of the graph, and all of a sudden, instead of remaining off and close to zero, this current begins to increase exponentially at some point, okay, drastically. And that point where um, the negative bias reaches such a big value that the current increases drastically, that's called the reverse breakdown effect. So if the reverse bias voltage across a PN gets too high, this is the reverse bias condition. If it gets too high, then the junction breaks down and the current increases rapidly. Okay, I increases rapidly even while V stays relatively constant, close to this breakdown voltage, negative VZ. Okay, VZ is defined as the reverse breakdown voltage of the PN junction diode. Okay, two different effects can cause this problem. Okay, there are two effects that cause this kind of breakdown. There is a Zener effect, okay, which is prevalent for voltages VZ less than 5 volts, and avalanche effect. An avalanche effect that takes place at voltages above um, 7 volts. So the idea is that the reverse breakdown happens because of Zener effect, that the onset of Zener effect is before the avalanche effect. Okay, the Zener effect sets in around 5 volts, while the avalanche effect sets in around 7 volts, and then the breakdown is a combination of both of these. Okay, VZ drops as doping levels are increased. So if I increase the amount of doping concentration, the VZ moves further and further closer towards the origin. So the breakdown voltage, as you can clearly see, it depends on the um, dopant concentration. If the dopant concentration is really high, VZ gets closer and closer to origin. Okay, so the idea of breakdown uh, in the forward biased condition, in forward bias, up around 0.5 to 0.7 volts, the transistor begins to turn on, and then the value of the current increases exponentially with the voltage. Okay, current has an exponential dependence on the voltage. Okay, applied voltage in forward bias. In reverse bias condition, so this is all forward bias. In reverse bias condition, the current is really small value for um, small voltages, reverse bias voltages. But then all of a sudden, the current begins to increase drastically because of the avalanche and the Zener effect. Okay, that's how a diode operates in forward and reverse bias condition. Typically, most often, we use the diode's non-linear exponential relationship in forward bias. Okay, so typically we like to use the forward bias. There are some applications where reverse bias is also utilized. Okay, then there is the depletion region capacitance. Okay, the charge stored in the depletion region varies with the bias voltage. Okay, so this is exactly similar to a capacitance. Okay, if you increase the voltage, then the amount of charge stored in a parallel plate capacitance is increased. Q equals to Vc. Okay, the charge stored in a capacitance is proportional to voltage, right? A parallel plate capacitance. Okay, if you think about it, the depletion region capacity, the depletion region charge here also increases as you increase the voltage. Okay, the built-in voltage, um, the amount of um, potential barrier. Okay, that also increases. The amount of charge also increases as you increase the voltage. Okay, so since the charge stored in the depletion region that varies with the applied bias voltage. That is exactly the phenomenon similar to um, capacitance. Okay, if I increase the depletion, um, if I increase the bias voltage, that increases the charge stored in the depletion region. So Q is proportional to V. Uh, so the operation is pretty similar to a capacitance. So you can think of a cap being inherent in a diode. Okay, Lord God um, put a capacitance into a diode. Okay, nature put a capacitance by the very design, by the very construction of the diode, by very definition, by increasing the voltage, bias voltage, we increase the charge, and that is fundamentally a capacitance. Okay, the depletion or junction capacitance is definitely non-linear and drops as the reverse bias voltage increases. As the reverse bias voltage increases, the capacitance, the charge stored, okay, is, as you can see here, it's not a straight line, it's a non-linear function. The slope of this is not constant, it's not linear. If it were to increase like so, I would call it linear capacitance. But as it turns out, the reverse bias voltage plotted on the x-axis and the charge stored is plotted on the y-axis. As you can see, this is a non-linear function. This is a non-linear function. Its slope is not constant. Okay, so when we look at that graph, at that spot, the slope of that guy gives the capacitance. Okay, the gradient coefficient.
Like,
Yes.
is there any region like why the capacitance decreases as the reverse voltage increases? Like maybe because the area of the depletion layer increases. That's why.
That's one of the reasons. But the thing is, if you look at the slope here, the slope seems to level off. As you can see, as you keep increasing the voltage, the slope of this guy begins to roll off. The slope of this guy begins to flatten. Okay, so there's a gradient effect. There's a gradient coefficient m, depends on how the PM, how the PN junction is made. Um, m is equals to 1/2 for abrupt step junctions, for junctions that have an abrupt step-like um, step-like um, coefficients, step-like voltages, and then for linear junctions where the doping is more linear and it's not abrupt change in doping concentration, then there's going to be a value of m equals to 1/3. Okay, so that's the idea. For linear junctions where the doping is more linear variable, the value of m or the grading coefficient is 1/3. For abrupt step junctions, it is somewhere half. For regular diodes that we use, it's somewhere in between a half and a third. Okay, so that's the idea of depletion region capacitance. Okay, we're talking about depletion region capacitance. There is also diffusion cap. Okay, it's also a diffusion cap CD, uh, where tau t is the time needed for carriers to recombine. So just like there was a thermal creation of electron hole pairs, typically what happens is um, typically what happens is um, the some charge carriers, free charge carriers, electrons, after some mean time, they tend to recombine. The excess carrier concentration in a forward bias junction varies with the applied bias. If we increase the applied bias, the excess carrier concentration increases. This variation in stored charge also looks like a capacitance. So the charge concentration, the carrier concentration, the number of carriers increases with the applied bias voltage. Okay, so that's the idea. When the charge increases, when the charge increases with the voltage, that's the fundamental operation of a capacitance. Okay, the charge carrier concentration here, the forward bias PN junction, increases with the applied bias. When we increase the um, forward bias value, that increases the charge carrier capacitance, and that replicates a capacitance action. Okay, this is called the diffusion capacitance. So we looked at two kinds of capacitance. There's a depletion cap, there's a diffusion capacitance. Okay, um, and it depends on the bias current um, and the thermal voltage, the mean transit time. Okay, mean transit time is the average time. Mean transit time is the average time that the charge carriers exist before they actually recombine. Okay, so as I mentioned earlier, there is a thermal, just like electron hole pairs are created spontaneously because of thermal energy. Electron hole pairs also recombine and annihilate, um, and, and, and that is also they release energy. That is also spontaneous, and the mean time between the charge carriers uh, recombining, being created and recombining, that mean time is called the mean transit time, tau t. So there are two kinds of capacitances: depletion capacitance and diffusion capacitance. Okay, so we looked at Let me quickly summarize the ideas here. Semiconductors are materials whose resistance can be varied over a wide range by adding controlled amounts of impurity atoms, okay, called doping. Silicon is the most widely used semiconductor device. When we put a p-type semiconductor and n-type semiconductor in contact, we get a p-n junction or a diode. Okay, when that happens, when P and N regions are combined together, at the junction, what happens is there is a depletion region. Remember the region in between the P and N right here. Okay, the white region, okay, this region, this is called the depletion region that forms on either sides of the boundary, okay, between the P and N. So this was initially all blue. But then, because of depletion, this became devoid of charge carriers. Also, all of this was initially gray, but because of diffusion of charge carriers, electrons, this became devoid of charge carriers. So this is depleted of the blue and gray charge carriers. And that's the depletion region. Okay, a depletion region forms because of diffusion, which creates a built-in voltage. Okay, electrons are diffused to the left-hand side, and the holes are diffused to the right-hand side.
So, like built-in voltage is kind of potential barrier that needs to be overcome.
Yes, yes. Built-in voltage is the potential barrier that is set up because of diffusion. Okay, and this built-in voltage prevents, like I mentioned, it's a self-limiting phenomenon. It opposes the further diffusion of carriers. Okay, and the other important thing that you want to remember is when a PN junction is forward biased, okay, it behaves as an as a closed switch. It is on. The PN junction forward biased, the diode is on, and the current flows, the current increases with exponentially with voltage. Okay, if you remember the IV characteristics, the current increased exponentially with voltage. Okay, forward bias. In the reverse bias, only a very small amount of current, IS, okay, in the reverse bias case. Okay, and then at really large reverse bias voltages, okay, the current increases drastically. Okay, forward bias, diode is on, it acts as a closed switch. The reverse bias, the diode is off, and it acts as an open switch. Okay, open switch, and this acts as a closed switch. Okay, PN junctions both have both depletion region capacitance and a diffusion capacitances. Okay, diffusion capacitance is coming from the fact that the voltage, as you increase the voltage, the um, the charge carriers increases. Okay, depletion is coming from the fact that the diffusion capacitance is increased, carrier concentration increases, and the depletion is coming from the fact that as you increase the bias voltage, that increases the depletion region charge. Okay, so whenever you see charge increasing in response to voltage, okay, then that's the phenomenon of capacitance. So these capacitances, depletion and diffusion capacitances, are artifacts that are built in to the diode. So a diode comes with an inherent depletion and diffusion capacitance. Okay, so that's the idea of diodes. Forward bias, the diode is on. Reverse bias, the diode is off. Okay, so we'll stop there. That's chapter number 3 for you. We'll take up this chapter of diodes now. We'll explore this chapter of diodes a bit more. Okay, so let's see. Just give me 1 second. Okay. Okay, so here is quickly what we are going to look at in chapter number 4. So far we looked at signals and amplifiers. This is chapter 1. Chapter 2, we saw op amps. Chapter 3 was semiconductors. And then chapter 4 is we're going to look at diodes. Okay, so far we are familiar with the idea of a diode. Diode has a P side and a N side. P side is shown with the arrowhead, uh, the broad side of the arrowhead, and then the N side is shown with the line over here. Okay, when I apply a positive voltage on the P side, negative voltage on the N side, that is called a forward bias condition. When I do the opposite, when I do the negative voltage here and the positive voltage here, that's called the reverse bias. In the reverse bias, diode is off, and in the forward bias, diode is on. This is what we looked at so far. Okay, so let's continue our discussion on the diodes about the PN junction diodes, our discussion. Okay, this is quickly what we are going to look at. We look at the large signal model and an analysis of forward bias diodes. We'll particularly look at the exponential dependence of um, ideal and constant voltage drop models. So we sometimes um, take into account the voltage drop between diodes, and sometimes we ignore that. As we can see, as you remember, the current in a forward bias diode is directly proportional to, is dependent on the exponential of the voltage that is applied between the PNN junctions. Okay, and then we look at a technique of solving by iteration. When you have a non-linear expression for current and voltage, how do you find the operating current and the voltage? There is a technique of solving by iteration or a successive refinement. Okay, so there's another technique of solving graphically, where it is about finding the intersection of um, load line and the IV characteristics. So we are going to look at that when we look at the large signal models. And then we're going to go into the idea of reverse biased Zener diodes, reverse biased diodes, okay? Where the diodes are not forward bias when you apply a negative voltage to the P type and a positive voltage to the N type. How does the diode behave? Okay, and then we look at the application of diodes as voltage regulators. Okay, we look at some diode logic circuits, limiting and clamping circuits, DC restorer, voltage doubler, so on and so forth. How do you generate um, power supplies, DC sources from AC current sources? When you have an AC current source, how can you generate a constant DC out of that? Okay, from AC to DC. That's the idea of a rectifier. And then we look at voltage regulators. And so a, a deeper look at the diode large signal and small signal um, models, and then reverse bias diodes, and then some applications of diodes. Okay, let's see. Here is the typical characteristics that we looked at for PN junction diodes. Okay, so the diode begins to turn on when its forward bias voltage goes to 0.5 volts all the way up to 0.7 volts, and then it increases exponentially. Okay, so this is something we saw. This is the forward bias. The reverse bias, the voltage, the current is almost close to zero throughout. And when it reaches a very large value, when the reverse bias voltage reaches a very large value, then the current begins to increase drastically. Okay, so this is something we discussed. Diodes conduct current when the junction is forward biased. So when the junction is forward biased, there is a current conduction. Okay, that is when the voltage that is applied on the P side is greater than the voltage that is applied on the N side. Okay, on the other hand, when the diode is reverse biased, there's only a tiny amount of current. There's only a small current, okay, called the saturation current, IS. Okay, if the reverse bias voltage exceeds the breakdown voltage shown in purple here, that's the breakdown voltage, then the current flow increases sharply in the breakdown region. There are two effects. There is the Zener effect, there is the avalanche effect that is responsible for this. Okay, something we discussed. And then I gave you an expression for the forward bias current. I is Is times exponential of V over Vt minus 1, where Vt is the thermal voltage, Kt over Q. This is something we discussed in the previous chapter, chapter number 3. Okay, the important thing to remember is the forward bias current is proportional to E to the V, the applied voltage. The applied voltage is V. Okay, the forward bias current is I. Okay, and this guy, the IS, is the reverse bias current here. Okay, so that's the idea, reverse bias current. So if I expand this further, if I'm going to zoom in on this region, okay, on that region to highlight the exponential behavior, that's exactly what is happening here. From 0.5 to 0.7 volts, this is the forward bias region. Okay, silicon diode turns on approximately at 0.5 volts. And until then, if you notice, the current is pretty close to zero. When the forward bias voltage, so in other words, if I apply a positive voltage of 0.5 here and a ground over here, around that potential, the diode begins to carry a significant amount of current at 300 Kelvin. Okay, the current here becomes interesting. Okay, and as I increases, okay, as I increases, the voltage increases. The voltage also does. But as you can see, voltage is only changing at a very small rate compared to I. The voltage is only going from 0.5 to 0.7 volts, while the current is increasing drastically. That is because of the exponential relationship between I and V. Okay? Current is proportional to the exponential of voltage, as you can see from the expression here. Okay? So voltage, for every 60 millivolt increase in voltage, the current becomes tenfold. Okay? So that's a pretty significant increase. So if the voltage goes from 0.56 volts to 0.5 volts to 0.56 560 volts. That is a 60 millivolt increase in voltage. Then the corresponding current is increased tenfold. Okay, so that's the idea of the 60 millivolt per decade relationship here. For every 60 millivolt increase in the voltage, the current is going to multiply tenfold. So voltage across the diode only varies slightly as current increases exponentially. And here what we have done is we have expanded, okay, um, certain parts of this graph, this part actually, and compressed certain parts of the graph to highlight the important parts. Okay, so the idea is that this is not to scale, this is just for us to realize that there is an exponential relationship. Okay, now there's also a temperature dependence. Okay, for a given, the bias voltage across the diode is carrying a constant current drops as the temperature goes up. Okay, so when the current is constant, okay, at a constant current there, right there, okay, for a constant current, as the temperature increases, T2 is at a higher voltage, a higher temperature, I'm sorry, T2 is a higher temperature compared to T1, which is a lower temperature. Okay, T2 is a higher temperature, T1 is a lower temperature. As the temperature increases, T2 greater than T1, the current flowing and the current remaining constant, the voltage, okay, the voltage corresponding to this guy, the bias voltage is smaller compared to this guy. If you think of this one as V1, as think of that two as V2, because this is corresponding to temperature T2, and V1 is corresponding to temperature V1. Okay, so this corresponds to a voltage of V2. So V2 is clearly to the left of V1, so V2 is less than V1. Okay, V drops by approximately 2 millivolts per degree Celsius. As the temperature increases by 1 degree Celsius, as the temperature increases by 1 degree Celsius, the voltage, the bias voltage drops by 2 millivolts. Okay, so the bias voltage across a diode, which is carrying a constant current, that drops significantly. Okay, in some applications, this can cause problems with thermal runaway. So to avoid problems, diodes are usually biased with a constant current source and not constant voltage. Okay, so typically what we always do is we take a diode, okay, and we ensure that by properly selecting an external circuit around it, we ensure that a constant current is flowing through it. That way, we can guarantee the current flowing through the diode, and then the current is the voltage is allowed to swing up and down. Okay, so there is some temperature dependence for a diode, the bias voltage of a diode. Okay, so the general practice is to bias the diode using a constant current source, not
So
a constant voltage.
the voltage drop, is it the voltage across the diode or it's the voltage applied to diode, like the
The
drop?
voltage across the diode, the voltage across the diode changes with temperature.
Okay.
Okay, so here is the ideal diode model, the large signal model. So on the left is a diode, on the right is a model. Model means approximation. Okay, I'm going to approximate the behavior of a diode using a switch. Okay, a switch. So as you can see, um, if you look at the current state of affairs, and when you see doctors saying that they're modeling the behavior of a particular disease or a particular epidemic or a pandemic, what they're actually meaning is we are trying to approximate the behavior using some mathematical expression. Okay, so a model simply means an approximation of a real world behavior. When they say they have a model of the disease flattening or the growth rate flattening, so on and so forth, the idea is that they're going to approximate the behavior using some mathematical terms that can provide some insights and some predictive power. Okay, even so, we take a real world diode, okay, and we create a model for it. Model is nothing but an approximation. Okay, in the simplest approximation, a diode is approximated as a switch. Okay, a forward bias diode is similar to a closed switch, and a reverse biased diode is similar to an open switch. Okay, so there is some current flowing in a forward bias diode. In a reverse bias diode, the current is assumed to be zero. So this is the approximation. Okay, so this is the approximation that we use to understand the behavior of a diode. Okay, so let me reiterate that using the um, notes here. Okay, the simplest model for a diode is an ideal diode model. So when somebody says an ideal diode model, they simply mean that the forward bias diode acts as a short circuit. In the forward bias mode, the diode acts as a short circuit, and in the reverse bias mode, the diode acts as an open circuit. See, there is an open circuit right there. Okay, there is no connection between the positive side and the negative side. It is open circuit. Okay, so the current flowing in there is approximately zero. But that's not the case. We know there is some reverse bias current flowing in there, IS, right? But we ignore that and we approximate this to be roughly zero. Okay, in the forward bias mode, we assume this to be a short circuit. Okay, a short circuit with zero resistance. So this is the ideal diode or the simplest diode model. Okay, ideal diode model in a forward bias. So let's look at an example here. So here is a resistance 1 kilo ohm connected in series to a diode. Okay, here is a resistance that is connected in series to another diode in the opposite configuration. Okay, connected in the opposite configuration. The example shown on the left has 10 milliamperes of current. Okay, this can be assumed to be forward biased. Okay, there is 10 milliamperes of current. Since the voltage across the forward bias diode is assumed to be zero. Okay, so in a forward bias condition, which is this side, okay, the voltage across that is a short. I replace this with a short, right? So it's going to be 0 volts. Voltage across a short. Remember, there is a short here. What is the voltage drop across a short? 0 volts. That is the assumption. Okay, the voltage dropped, and that is a pure approximation. I'm neglecting the built-in potential. Okay, so in the simplest form, a diode that is forward biased is approximated to be a short, with 0 volts dropped across it. Okay, when 0 volts is dropped across the circuit on the right, that's the circuit on the left. Okay, the circuit on the right, I'm assuming this to be reverse biased. Okay, I'm assuming this to be reverse biased. Because this is reverse biased, what happens is, think about it, this acts as an open circuit. Okay, like I mentioned, go back up. Okay, reverse bias is assumed to be an open circuit. Okay, a diode that is reverse biased is assumed to be open circuited. So that's exactly what I'm doing here. An open circuit has no current flowing through it, and that explains the 0 milliamperes current flowing in here. Okay, because this is open circuit. Okay, so that's the idea.
So we
Yes.
can basically say is that diode act as a conductor when it is forward biased, or can act as an insulator or something when reverse biased.
Yes, exactly. The diode acts as a off switch or an insulator with an infinite voltage, infinite resistance across it, insulator at reverse bias condition, and then it acts as a short circuit. Okay, it acts as a short circuit when it is open, when it is forward biased. Okay, and it is on. Okay, so this is the simplest approximation. Okay, so what I have done is, in this case, in the case of a reverse bias, I assumed it to be open circuit. Therefore, the amount of current flowing is 0. And in the case of a forward bias, I assumed to be a short. So the current, I can look at the voltage drop at that terminal. Okay, so that's the idea. For the example circuit shown on the left, the current is 10 milliamperes. Okay, 10 milliamperes. Since the voltage across the forward bias diode is assumed to be 0 volts, okay, okay, I can see that the current is, when this is 0 volts, when the voltage here is 0 volts, that goes to ground, 0 volts as well. So the 0 volts that I apply here shows up on that node as well. Okay, so I can find out the current to be 10 minus 0 by 1 kilo ohms to be 10 volts. Okay, or 10 milliamperes, sorry. Okay, so I arrive at a value of I equals to 10 milliamperes by assuming this diode to be forward biased and making it a short circuit. Okay, so that gives me a value of 10 milliamperes for the current. The circuit on the right, on the other hand, the diode is assumed to be an open circuit, reverse biased. Okay, and it's easy to see why it is reverse biased. The positive side is connected to lower potential, and the negative side is connected to higher potential. So it's easier to see why it is reverse biased. Okay, in this case, the positive side of the diode is connected to the higher potential, plus 10 volts. The negative side of the diode is connected to the lower potential. So it is reasonable to assume that this diode is forward biased. So this diode is forward biased. This diode is reverse biased. Okay, so let's see. The diode on the circuit on the right is assumed to be an open circuit, and the full 10 volts appears across the reverse biased um, diode. Okay, so this is assumed to be 10 volts because there is no current flowing in here. So there is no voltage dropped here. So the 10 volts that I apply here is going to show up there. And then this is going to be an open circuit. Okay, this is going to be an open circuit. Okay, an open circuit right there. And all the 10 volts is going to show up across that open circuit there. Okay, so this is the idea. Questions, please. Okay, so this is the general approach that we follow when we are solving the problems. Okay, to solve problems, okay, first we assume diodes are either on or off. Okay, and I'm going to show that using an example to you. Okay, we assume the circuit is going to be, the diode is either on or off. Then we follow our analysis, and eventually check our assumptions. Do our results validate or invalidate my assumption? Okay, this is what I will do. So assume, analyze, and then check. Okay, so sometimes our analysis, when we do the check, will tell us that our assumptions are wrong. So we'll go ahead and rearrange, modify our assumptions. Okay, and then so this is the general approach. The same approach is true for diodes. And when we go to MOSFETs, okay, even for MOSFETs, the region of operation, we typically assume saturation, and then we make our analysis and check to see if our assumptions are correct. Okay, that's the general procedure that we will follow. So let's look at that implementation of that in an example. Okay, so let's see, I have a problem here that looks like this. Okay, that looks like the one on the right. There is a diode, there is another diode. There are two diodes here, and there's a negative voltage applied, there's a positive voltage applied. And I'm interested in calculating the voltage V over here. What is the voltage V? Okay, so what's the voltage V that is applied here? Okay, so what I'm going to do is, and I don't know, how do I know whether this diode is forward biased or reverse biased? If I know it is forward biased, I'm going to represent it with a short. Okay. Similarly, I don't know whether this is a forward biased or a reverse biased diode. If I know a particular diode is reverse biased, let's say if I knew ahead of time that D2 is reverse biased, then I'm simply going to open circuit it and find out the voltage across these terminals. Okay, but I don't know, I really don't know what these voltages are. If I knew the voltage here and here, then I would know whether the diode D1 is forward biased or reverse biased. Similarly, if I know the voltage here and here, then I know D2 is forward biased or reverse biased. I don't know now. As of now, I don't know whether D1 and D2 are forward biased or reverse biased. So in order to solve this
So
problem,
I have a question. So like for the diode one, like its positive side is connected to ground. So isn't it reverse biased?
we don't quite know. The negative side, if you think about it, it is connected to negative 10 volts. What if there is a negative 5 volts over here? If there's a negative 5 volts, then the N side is connected to negative 5, the P side is connected to 0. So the P side is more positive than the N side. So there is a
Oh,
possibility that this could be forward biased.
okay.
You see what I mean?
Yes.
So until I know the numerical value of VB, okay, what is the value of VB, voltage over there? I really do not know whether this is forward biased or reverse biased. Okay, if I know the numerical value of the voltage there, then I already know the voltage there, which is 0. Then I can say whether the diode is forward biased or reverse biased. Okay, so here is the technique I'm going to use. Okay, the problem is assuming the diodes are ideal. What does ideal mean? When the diode is on, The voltage drop is 0. Correct. It's a short circuit. When it is off, the voltage drop is infinity. The voltage drop is, or the resistance is infinity, or it is open circuit. Okay, that's the problem here. So let's see how I begin. So in these circuits, it is not obvious. It may not be obvious at first sight as to whether one of these diodes is on, or none of these diodes is on, or both of these diodes is on. So in this case, what we make is we make a plausible assumption and proceed with the analysis and then check. Okay, so we make a plausible assumption and then we check. Okay, so the assumption that we make is, like I mentioned, so this is at a 0 potential, and if I assume this to be at a negative potential, I'm assuming this diode is forward biased, and I'm also going to assume that this diode is forward biased. So in this case, to begin my analysis, I assume both diodes are forward biased. Okay, both diodes are conducting. So that is the assumption I make. We shall assume that both diodes are conducting. Okay, when both diodes are conducting, so let's take a look. Let's go back. The assumption is that let me not worry about D2 for now. Let me just look at D1. Okay, D1 is forward biased. That's the assumption. Therefore, this should be a short. Okay, when this is a short, you think about it, then the ground that I apply here is going to show up as a 0 voltage here, right? Okay, so the obvious conclusion is from the ideal behavior, um, it should tell me that this voltage is 0 volts. Okay, because D1 is shorted. Okay, that gives me that this potential is 0, and what happens to I2? So, and D2 is on as well. So as a result, what happens is I further assumed that D2 is on as well. So that makes this potential 0. Okay, because D2 is assumed to be on, so I can replace that with a short circuit. So this becomes 0 volts. So now I can calculate the value of ID2, which is the current flowing in this branch, is 10 volts minus 0 volts by that resistance, which gives me a value of ID2 is 1 milliamperes. Okay, so it tells me, if you think about it, it tells me that ID2, the current flowing into this branch, is 10 milliamperes. Okay, that's the value of ID2. Okay, now writing the node equation at B, if I write the node equation at B, I, the sum of the currents I plus 1 equals to 0 minus of minus 10 by 5. So adding the currents through both of these branches, I plus ID2 should equal the current flowing into this branch, which is 0, because that is assumed to be a short circuit, 0 minus 10 volts by, so this gives us ID2 equals to 2 milliamperes. So this tells me that the current results in a value of I equals to 1 milliamperes. This tells me that I is, when I solve this current equation here, is everybody with me? Are you with me? Okay, so this equation is simply an application of KCL at this node. Okay, the current flowing in is the sum of I and ID2. I is left as ID2 is 1 milliampere. So I plug in 1 over there. That should equal the current flowing in this branch, which is 0 minus 10 volts over 5 kilo ohms. That's exactly what I have done here. So from this, it gives me a value of I equals to 1 milliamperes. Okay, it gives me a value of 1 milliamperes, which is absolutely a silly result. Why is that the case? If this is at 0 volts and this is at 0 volts, I cannot have a current of 1 milliamperes flowing in this diode. Because if this is a short circuit, this is ground, and this is assumed to be ground, then I cannot have a voltage of a current of 1 milliamperes now. Okay, so thus D1 is conducting as originally assumed, and the final result is I equals to 1 milliamperes for 0 volt. For the circuit in 4.6b, we assume that both diodes are conducting, then VB equals to 0 and V equals to 0 volts. Okay, V equals to 0 volts because this is conducting. So we assumed that this is at ground. So this is at ground as well. Okay, so V is 0 volts. Okay, so that's the assumption. The current in diode 2 came out to be 2 milliamperes. The node equation, if we write the node equation at V, okay, so that's the answer that we acquired, which yields a value of I equals to negative 1 milliampere. So the idea is that when we start with the assumption, okay, so we did the node equation at B, okay, and then we we obtained the equation for current ID2. Okay, we obtain the current equation for ID2. That is not consistent with the node equation at B. Okay, this is not consistent with the node equation at B. So once we plug in the value of I equals to 1 milliamperes, this is giving me inconsistent result. Initially, I got I equals to 1 milli, then I got I equals to negative 1. So this is not possible. So the only conclusion is that the assumption that both diodes are on is not correct. So we start again by starting a new assumption. Okay, so we started D1 is on and D2 is on. Both of these are forward biased. So we get an inconsistent result directly as a consequence of that assumption. So now we are going to modify my assumption. I assume that D1 is off and D2 is on. Okay, when I assume D1 is off and D2 is off, then the current in D2 is given by plus 10. So when I assume this is going to happen, so when I assume the new assumption, so let me show you the new assumption here. The new assumption is that all of this is open circuited. Okay, so that is all completely out of this circuit because I assume this diode to be off. Okay, and then I assumed D2 to be on. Okay, now what I can say is I have a resistance here and I have another resistance here. Now I should be able to write the expression for V. Okay, I should be able to write the some expression for V using this assumption. Okay, ID2, which is the current here, ID2, that current is plus 10. So the voltage that is applied over here. So that's the current E10 minus 10 by the total of 10K plus 5K, which is 15K. Okay, so the voltage applied on the very top minus the voltage applied on the very bottom by the total resistance. So it gives me a value of ID2 equals to 1.33 milliamperes. Okay, once I get the value of ID 2 to be 1.33 milliamperes, I can get a value for IB. Okay, once I have a value of ID2 to be 1.33 milliamperes, I should be able to calculate the voltage drop across that guy, which is nothing but if this is a short circuit, this is going to be ID2 is current 1.33 milliamperes is flowing in here. This guy times this guy gives me the voltage drop across that resistance. Okay. So D1 is reverse biased and D2 VB, the voltage at VB can be obtained using the Ohm's law over here. Okay, so once I get IB, that's the current flowing in there, and the voltage times so negative 10 is the voltage applied. You think about it, negative 10 is the voltage applied, and 10 times 1.33, 10 times 1.33 is the voltage that is over here. So I can obtain the value of the voltage, this guy here, to be the voltage VB to be negative 10 plus the voltage drop across that resistance. Okay, so that's the idea. Now, this is consistent. Thus, the D1 is reverse biased as assumed, and the final result is I is 0 volts and V is 3.3 volts. So V has been found to be 3.3 volts. ID2 has been found by using the Ohm's law. The total voltage applied across the top 10 ohms resistance, 10 kilo ohms, and the bottom 5 kilo ohms, 15 kilo ohms resistance. Okay. So the initial assumption was that this is on and this is on. This led to an inconsistent solution that I1 is 1 from one equation and I1 is negative 1 from another equation. So that guy is inconsistent. It can't be true. So I revised my assumption that D1 is off and D2 is on. Then I arrived at a solution that is consistent. Okay. So that's the idea of solving. Okay, assume both D1 and D2 are forward biased. Then that gave me an inconsistent solution. Then assume D1 is off and D2 is on, and that gave me a more consistent solution. Okay, so this is the ideal model was like this. Okay, so ideal diode model was when there is no forward bias, the current flowing is 0. When there is a forward bias, the current it's a short circuit. Okay, now we augment the diode model a little bit to incorporate the built-in potential. Okay, so the diode, the assumption in a constant voltage model in a forward bias condition is the diode is not going to have any current until we hit 0.7 volts. And once we hit a 0.7 volts, it's going to behave like a short circuit. Okay, so the modeling of ideal diode earlier was that it is on, the voltage drop is 0 or a short circuit. Okay, here what we do, so this is the ideal model, ideal diode model. Okay, here we assume a constant voltage model. In this case, when the diode is on, we assume the voltage is to be 0.7 volts, or we assume that it behaves like a battery. Okay, so a better diode model which takes into account the built-in potential, and it gives us more accurate results in the circuit analysis, is the constant voltage model. Okay, it's called a constant voltage model. The model assumes the diode is a short circuit when forward biased and an open circuit in the reverse biased with a voltage source in series. Okay, that part is not shown here, that's missing here. But the assumption is that when the diode is forward biased, it's a short circuit with a, it's not exactly a short circuit, but it's a battery. The diode is assumed to have 0.7 volts across it when it is on. Okay, and 0.7 volts is a reasonable value to assume for most diodes. Okay, so earlier, if you think about it, here is a comparison of both the approaches. Okay, on the top here, I'm trying to find the current through the diode using ideal diode model. Okay, here I'm going to find the current, okay, using the constant voltage model. Okay, there are two problems that I'm going to solve here for the exact same circuit. Okay, let me show you the first problem. In here, I assume that this diode is a ideal diode and there is no voltage drop across it. Okay, and this is ground. What is the value of ID? ID is, this guy is 0 volts, this guy is VDD or 5 volts. Okay, VDD is given to be 5 volts. Oops, VDD is given to be 5 volts. Okay, and R is given to be 1 kilo ohms. So in order to find ID in ideal diode model, ID is given to be 5 volts minus 0 volts over VDD, which is over RD, sorry, which is 1 kilo ohm. Okay, 1 kilo ohm. That gives me 5 milliamperes. Okay, this is ideal diode model. Now see, look what I'm going to do for not the ideal diode model, but the constant voltage drop model. For the constant voltage drop model, I'm not going to replace this diode with a short. Rather, I'm going to replace it with a voltage source of 0.7 volts. Okay, this diode now is replaced with 0.7 volts. Now, if I have to find the current here in the constant voltage drop model, so constant voltage model, the drain current or the diode current ID is 5 volts minus, it's not 0 volts anymore. The potential here is 0.7 volts. So minus 0.7 volts by 1 kilo ohm. So it's going to give me 4.3 milliamperes. So this is more accurate, okay, compared to the 5 milliampere approximation. Okay, to get the most accurate value, we must use the exponential. The perfect way to do that would be to use ID, exponential equation for ID, but we are going to approximate ID using two models. One is a constant voltage drop model, where I assume this to be 0.7 volts, or an ideal diode model, where I assume VD to be 0 volts. Does that make sense? So we looked at two models. Okay, if you remember, I'm going to give you an example. I was following the other day the press conference that Dr. Anthony Fauci was giving. Okay, and he said, referring to the modeling of the pandemic disease that is prevailing, he said, these estimates are close, but the models and their predictions are only as good as the assumptions that we put into these models. Okay, so that is illustrated, the phenomenon that our predictions and our results are only as good as the assumptions that we put into these models. That idea is illustrated here. using two models. In one model, we assume the voltage drop across VD is 0. So that's the ideal model where VD is assumed to be 0. And in the next model, we assume VD to be 0.7 volts. Okay, we assume VD to be 0.7 volts. That's the second model. Okay, this is model 1, where the assumption is VD is 0.0 volts, and the model 2, where the assumption is that VD is 0.7 volts. Okay, so that's the assumption using constant voltage diode model. And it turns out that for most practical purposes, the constant voltage model is much more accurate, but it's still not 100% accurate, but it is a reasonable approximation of the real world behavior. Questions, please. Okay, and then what we did was to find the value of VD, ID using VD minus, this is VD minus VDD, or VDD minus VD over R. Okay, so that is the idea. So the idea is that the current that is flowing through the diode is exactly same as the current that is flowing through the resistance, and therefore by finding the voltage that is the current that is flowing through the resistance using Ohm's law, I can see that the same current is flowing through the diode, and that will give me a value of the diode current. Okay, makes sense. In this case, 4.3 milliamperes is a much more accurate value. So here is another technique. There are two techniques that I'll show you. Solving by iteration to get the exact value, okay? Solving by iteration and solving using load line analysis, okay? So if we are to determine the current and the voltage VD for the circuit in 410, okay, with a VDD of 5 volts and a R of 1 kilo ohms, assume that the diode has a current of 1 milliamperes at a voltage of 0.7 volts. Okay, that is the assumption. So to begin the iteration, we assume VD equals to 0.7 volts, and using the above equation, we define ID to be VDD minus VD over R. Okay, then using this approximation, using this as an initial guess, we go on successively improving the value of VD and ID. Okay, so we plug that numbers in and we get an expression for VD to be VT times ln of ID over IS. Okay, we assume ID is given to be, it was given that ID is 1 milliamperes, VD is equals to 0. amperes, 7 amperes. So we can find the value of IS. Okay, so we know the value of ID is given to be 1 milliamperes, and we know the value of VD is given to be 0.7 volts. We found IS to be 2 femtoamperes. Okay, now what we do is we start with a guess. So the general procedure for to solve for ID using iteration is we guess for ID, which we came up for a value for that to be 4.3 milliamperes. Okay, so this is the initial guess that we came up with. Okay, then we solve for VD using the equation VD equals to VT ln ID over IS. So once we had a rough estimate for ID, then we calculated a value for IS to be 2 femtoamperes. Now using that 2 femtoamperes, and then we know VT to be 25 millivolts, and then using a value of ID to be 4.3 milliamperes, we get a new estimate for VD. Now, once we have a new VD, we find a new ID. Okay, then we come back and plug that ID in here. Okay, let me illustrate that using the example here. So initially ID was given to be 1 milliamperes and VD was given to be 0.7. Using that, we calculated IS to be 2 femtoamperes. Okay, then we obtained a value for VD to be 7.38 milliamperes. So then using these numbers, we improve upon the value of VD from 0.7 to using this equation here. Okay, using this equation here, we obtain the value of 0.738 volts. Okay, now what we do is we plug that into the equation here. Okay, we plug it into that equation, and then we get a second guess for ID to be 4.261691 milliamperes. So our initial guess was 1 milliamperes. Then we arrived at a value of 0.7. Using that, we found out ID to be 4.3 milliamperes. Okay, then we adjusted the assumption of VD to be 0.738. Using that, I refined ID to be 4.26. Then the IDs came out to be, so I keep improving, iterating using the same steps. Okay, we repeat steps 1 to 3. Steps 1 to 3, guess a value for ID initially, then we keep successively refining ID. So we guess a value for ID, and then we get a new value for ID. Then we go back and use that new value as the new guess and get the value of VD. From that VD, we calculate a new value of ID. So from VD, we calculate a new value of ID. From ID, we calculate a new value of VD. So we continue to do this until the two successive values of ID are exactly the same. In other words, even by successively repeating this step over and over again, the value of ID is not changing. Take a look at this. Okay, in step guess 3, the value of ID came out to be, at the end of that, 4.2619225 milliamperes. Then we went through the whole process again. What's the new value? That's exactly the same. So in other words, when two consecutive guesses are identical or within very small error limit, then we call the solution has converged. Okay, so this is the process of finding the exact operating value using iteration. Okay, we'll stop here. We'll come back tomorrow and look at another technique using load lines. Okay, and then we'll solve for an exact solution. Okay, so so far what we have seen is to use a model, a constant voltage diode model, to come up with an estimate, ID equals to 4.3 volts, then successively refine that using iteration technique. Okay, so we iterate over and over through steps 1 to 4 to arrive at the final solution. Okay, we'll stop here. We'll come back to look at another technique, load line analysis technique, in the next class. Okay.
Professor?
Yes.
Why did you use 26 millivolts for VT on the equation above?
Yes.
One
Remember,
slide up.
VT is KT over Q. K is the Boltzmann constant, T is the room temperature, and Q, little q, is the charge of an electron. So all of these are known values. If I plug that in, let me go back a touch to chapter 3. And then I said, you should remember this KT over Q friend somewhere. Okay, VT is KT over Q, and it comes out to be 26 or 25 millivolts when you plug in the values. Okay, somewhere in here, right here.
Oh, okay. Thank you.
300 Kelvin at room temperature, its value is 25. Okay.
Okay. Thank you.
Yep.
Professor, if we have doubts
Yes.
with the lab, we can talk tomorrow.
Yeah, we can talk during the lab time tomorrow. I'll be glad to put you in a separate room and we can discuss that.
Okay.
Okay. Other questions, please. All right. Okay. So pretty good. I'll see you folks tomorrow then. I'll see you folks tomorrow, and then we'll finish this chapter on diodes.